In investigation 1, we're going to be working on a problem in which we have this launcher which simply drops ball B straight down while simultaneously firing A horizontally, and so it will land somewhere over here. Your teacher asks you to predict which ball will hit the tabletop first when the lever is activated. You're to make a prediction and justify your answer in a clear, coherent paragraph-length essay. What we're looking for in this paragraph is that you understand that while the mass is different, mass plays no role in the acceleration due to gravity. The second thing that we're looking for is that you understand the equation that's going to govern the amount of time it takes to hit the ground is d in the y direction equals v initial in the y direction t plus 1/2 a t squared. So, provided that both balls have no initial velocity in the y direction, and provided that they both have the same acceleration due to gravity, then their times would be the same. In part B, we want to figure out how fast the ball is going to be fired. To do this, I can think of two ways. First, I thought, if I take the area under the graph for the 0.2 meters that the spring is compressed, then I'll know the work done on the spring, which will become the potential energy stored in the spring, which will become the kinetic energy of the ball, and I can calculate the speed. So the area here is what I'm going to find. It's going to equal to the work. So the work equals 1/2 the base times the height, which is 1/2 0.20 meters times 4 newtons, and I get 0.4 joules. Next, I'll use this as the kinetic energy to figure out the speed at which it's launched. So 0.4 joules equals 1/2. The mass of this guy was 0.02. I'm sorry, 0.02. V squared turns out to equal 40. So V is 6.3 meters per second. Another way we could have done it is use the graph to find the spring constant. And to do that, we take the slope. So change in y, I'll do 4 newtons minus 0 newtons over 0.2 meters minus 0 meters. And I'll get 20 newtons per meter. Now I'll relate the kinetic energy of the marble once it's fired to the potential energy stored in the spring. The halves can go out. We have 0.02 kilograms times v squared equals 20 newtons per meter times 0.20 meters squared. Again, we'll get v is equal to 6.3 meters per second. Either way is perfectly acceptable. In part C, the launcher is positioned such that the balls are 0.65 meters above the tabletop. So from this, we know we're going to have a horizontally fired projectile problem. And we know that in the y direction, the distance in the y that is going to fall is 0.65 meters. We also know the acceleration in the y direction is 9.8 meters per second squared. And the initial speed in the y direction is 0 meters per second. In the x direction, we know that it's fired at the 6.3 meters per second we found in part B. And because there's no acceleration in the x direction, this is also the average velocity. So the first thing I'll do is I'll figure out how long it's actually in the air for. So d in the y equals VIT plus 1/2 AT squared. V initial was 0, so I can cross out that term. And so the time comes out to be 0.36 seconds. Next, I'll use my x information to figure out how far the ball went. So it was traveling at 6.3 meters per second for a time of 0.36 seconds. And so the distance it travels turns out to be about 2.3 meters per second, which is less than the 2.4 it actually traveled. Now, one reason students commonly will give for errors in experiment is friction or air resistance, but in this case, the air resistance would have made it go less than 2.3 meters, so that's not a valid answer. The answer that I was thinking was maybe the student started with this launcher being a little bit higher than the 0.65 meters that they measured. If it was higher, the ball would stay in the air a little longer, and therefore would go further. Another answer is, what if this launcher was a little bit at an angle? Then also it would go a little further than you predicted. There are other possible answers, but these are the two that I thought of.